Hey guys, welcome back to another episode of Tumor Teaches. So today's topic is going to be an introduction to organic chemistry, which it's definitely a bit of a scary topic. But to be honest, at this level, you're not going to be covering much. If I'm going to be honest here, but without with that aside, let's just get right into it. So organic chemistry is considered to be the chemistry of carbon-containing compounds. The reason why carbon gets its own type of chemistry is because it's a very special element. It can form four covalent bonds, which, yeah, that's kind of okay, fine. So why isn't group 14 special? But the reason that it stands out is because there's a variety of structures, a variety of bonding patterns in which carbon can take. Um, it can bond with itself. It can form these unique structures, and since carbon's like structures and all that stuff are so widely varied and vast, um, we give it a special designation. Now, the reason it's called organic is just for historical reasons. Originally, they thought that only living things could produce these carbon compounds. Um, so organic life, it just makes sense. I don't know. It's just a convention that's stuck there, but that's sort of brief overview on the history as to why it's important and sort of where it came from and where it's not where it's going necessarily, but where it came from. Now we can first let's start by breaking it down, categorizing things, and the simplest form, the simplest organic molecule that you'll ever encounter is hydrocarbons, which are compounds that only consist of carbon and hydrogen. They're the most basic type of compounds, and generally all other compounds are considered derivatives of hydrocarbons. We can further categorize these into acyclic and cyclic molecules. Cyclic meaning they form, polygonal structures, and acyclic meaning they don't. They just consist of a line with some branches coming off of it. Um, so here's an example of some acyclic hydrocarbons. This one and this one. Whereas these are cyclic ones. You can see how they have sort of polygonal structures. Um, polygonal structures. So here's a ring. Well, we all call them rings, but this is a hexagonal ring. This is a pentagonal ring, and what you'll notice here is that okay, there's some double bonds here and here, and that actually leads us to our next categorization, where we can have saturated and unsaturated hydrocarbons. Saturated hydrocarbons only contain a single bonds, whereas unsaturated contains one or more double or triple bonds. So these are saturated hydrocarbons. Notice here how there's only single bonds, and then with the unsaturated ones, there's double or triple bonds. Well, there's only doubles here, but you can have triple bonds within them as well. Um, Now we can further split the tree off into. We can further split the tree into for acyclic hydrocarbons. These are essentially the next little bit here. Essentially describe the same thing. It's just we use different terminology for for ring structures versus um, for cyclic structures versus acyclic structures. But we can have unbranched and branched um, hydrocarbons, where unbranched hydrocarbons contain all have their carbon atoms in one continuous chain, whereas branched hydrocarbons have they have they have some carbon atoms that are not part of the longest continuous chain. Uh, branched branched hydrocarbons at least have will have at least one carbon atom that is bonded to uh, three or four other carbon atoms, and generally, if they're not part of the longest continuous chain, they're called branches. And you can have a similar sort of thing for cyclic hydrocarbons, where if where on the outside of the ring you generally have hydrogen atoms, and if you don't have a hydrogen atom, you call that a substituent. If you have something else there, and if it's just hydrogens on the outside of the ring, it's unsubstituted. So it's a similar sort of phenomenon. It describes more or less the same thing. We just use different terminology depending on the type of hydrocarbon, if it's cyclic or acyclic. So notice here, although you may think this is branched, note that this is in fact one sort of continuous chain. You can The way I was taught is that you can draw one line without it sort of like you can draw one continuous line and catch all the carbon atoms, whereas here if I do this, I will always miss one of them, or if I did probably the most straightforward on that. Notice here how this carbon does not lie on the line, the straight line that I draw. I'd have to take my pencil off to catch that particular carbon. I'd have to, like, it can only be a straight line with 90-degree turns, more or less. I guess that's a good way of if you can draw it with only 90-degree turns, then yeah. Now, so here is also the same thing. Here's 5 hydrocarbons. Here's 5 carbons. Or alternatively, if we wanted 5 carbons, this is 1, 2, 3, 4, 5. Notice here how you're always missing something. Right. So, yeah. The next thing we need to talk about, the next thing that we can go on to are structural isomers. Now, isomers are just, iso is a prefix meaning same, and mer, well, that's just, well, I don't know what mer is, but iso is a prefix that means same. So isotonic, same tonus, same concentration, for those that study biology. Yeah, isomer meaning same something, and in this case we can talk about, well, the higher levels are going to go straight quite a bit into isomerism, but generally the standard levels will only go into structural isomerism, which are molecules with the same molecular formula but have different Lewis structures. And then when we describe organic compounds, we can either use molecular or empirical formulas, like as we did so far, or we can go into a new type of description, since you know, the same molecular and empirical formulas can be used for multiple different Lewis structures. So now we will introduce the structural formula. So the structural formula are formulas that unambiguously show the bonding arrangements of the atoms within a molecule. So it shows sort of what the chemical structure looks like compared to only listing the types of atoms and how many of them there are in a molecular formula. For instance, a structural formula shows exactly how they're bonded together. So we can draw just full Lewis structures, or we can use condensed structural formulas, or we can use skeletal formulas. So this one, you already know how to draw a Lewis structure. These ones, I'm not going to go into too much depth, but because they're pretty intuitive, I would say. So you just draw CH3, CH2, CH2, CH3. So you have a CH3 group bonded to a CH2 group, bonded to a CH2, bonded to a CH3. Like, that's pretty intuitive to understand. Or you could alternatively do it like that. Okay, these brackets here just indicate that there is a repeating unit, and then this number here this is the repeating unit. This is how many times it repeats, and then with CH3s on the end of it. Or alternatively, you could have this and then a C bonded to 2 CH3s. Remember, there's 2 CH3s here bonded to this carbon, and then you would draw an H there. So sort of, it's pretty simple. It's pretty easy to get the gist of it. The only thing I would caution you is with these brackets on the end here, be careful. If you need to draw out full Lewis structures, by all means draw it out like fully, but I think generally this is generally why people don't like fully condensed formulas. There's another way to do it where you can show it more clearly. Oh, okay, this clearly, one of these CH3s has to be bonded here. But regardless, now we're going to go into the skeletal formula, which basically some people actually really like these, and I myself do kind of like them. Basically, you just draw lines, and at the ends, like these vertices, are a carbon attached to however many hydrogens it takes to fulfill the octet rule. So this is a full structural formula of C6H12, where this is the skeletal formula, where you can see each vertice is a carbon attached to, in this case, 2 hydrogens, because that's how many it'll take to fill the octet rule. You can use a combination of each. You can use combinations of each structure to sort of represent the structure of an organic molecule. you don't have to stick to one way. So for example, generally in a text you'll see this because this structure here is just nicer looking than this, and it's more clear what it communicates. And or here you'll notice how there's this little line here and above with the CH3, because here it's more clear than this because it shows, okay, one of these CH3 groups is bonded to this carbon, the central carbon here, rather than here where it's not that clear. And here generally the reason why we didn't use a structural formula here is because it's cyclic, and we wanted to show that polygonal structure, and that's what skeletal formulas are really useful for. If you have cyclic molecules, it's much easier to interpret a skeletal formula than it is a condensed structural formula. You'll generally tend to use condensed structural formulas for things that are acyclic hydrocarbon chains. Now we need to talk. Let's talk about a special type of a special type of cyclic molecule, which is benzene, C6H6. The benzene ring is a significant structure within organic chemistry partly because of its delocalized electrons, and that, as a result, allows it to undergo it undergoes specific types of reactions, which for the higher levels you'll see this quite later on, but it's a special compound, so it's worth giving a bit of a sidetrack to. So the common representation of benzene is like so, and this circle here just shows the delocalized ring of electrons, whereas you can see here, rather than drawing out a resonant structures, it's easier just to show this ring. And then arene is a organic molecule that has at least one benzene ring as part of its structure. For some reason, the IB wants you to know about chemical and physical evidence for its structure, so for a long time it was just thought to be cyclohexatriene, cyclo meaning ring, hexa meaning 6, and tri meaning 3, and ene meaning double bonds. So putting it all together in a name that might be of more significance to you, a 6-membered cyclic molecule that has 3 double bonds. And this interpretation is actually incorrect because benzene has resonant structures, and as a result of its delocalized electrons, we get the modern structure. We get the modern interpretation of its structure today. So the first piece of evidence is that benzene is more symmetrical than cyclohexatriene, because benzene has resonant structures that has a bond order of 1.5, whereas in cyclohexatriene it's alternating 2 and 1, 2 and 1. So in other words, all the bonds in benzene are the same length, whereas in cyclohexatriene one bond is shorter than the next bond, which is shorter, and it looks like a really weird hexagon, whereas benzene looks like a proper hexagon. The next bit of evidence is benzene undergoes, well, it specifically goes electrophilic substitution reactions and not electrophilic addition reactions. Because its ring is really stable, it'll therefore only substitute things, and it won't add things to the ring to do it. Whereas if it was cyclohexatriene, it would undergo addition, and it would have 2 double bonds, and then rather than 3. Whereas the ring is intact always. And then 3 here, it sort of jumps off the last point. It's more stable than cyclohexatriene because the ring is super strong. So here, the addition of hydrogen for benzene to make it C6H12 and not C6H6 experimentally in the lab was measured to be this, whereas for cyclohexatriene it is theoretically calculated to have been that. The next thing, I want to just check how long this video has been going on. Wow, this is a long video. The next thing I want to talk about is homologous series. Homologous series are compounds which only differ by some which only have an incremental difference in some parameter. So, for example, the alkane series and the alkene series. Here is an example of a homologous series. Here you can just see that we're adding more CH2 groups in the middle and just making them longer. And interestingly, the members of homologous series have similar chemical properties, and gradually they change in their physical properties. So here, for example, we can take the boiling point of various alkanes. And if we measure the number of carbon atoms in the main chain as a function of their boiling point, if we take the boiling point as a function of how many carbon atoms are in the longest chain, we can see here that it gradually increases because there's more van der Waals forces, because there's more electrons and it's more polarizable. Lastly, we go into naming. These are some naming conventions that you are expected to know for the IB. For alkanes, they're denoted by the formula CnH2n plus 2, whereas n is an integer, and a lot of these you just have to sort of memorize. So there are a set of naming rules for organic compounds that are special, that contain prefixes and suffixes. These are the prefixes that you're expected to know, and these prefixes describe how many carbon chains are in the longest chain. How many carbons long is a particular chain. So this is methane, this is ethane, propane, butane, so on and so forth. And we can see here 1 carbon, 2 carbons, 3 carbons, 4 carbons, and so on and so forth. These endings here, you just have to memorize. There's no short way around it. Generally, I think flashcards are the way to do it. And so when we name acyclic alkanes, which is what you're responsible for, there's a set of rules that you're expected to do. One, which is locate the longest continuous chain of carbon atoms in the molecule. The last or potentially only part of this name consists of a prefix indicating the length of the main chain, followed by the suffix "ane," which indicates fully saturated. Then you're going to find all these branches connected to the main chain, and if it's a branch, you add the suffix "ul" to it. Assign each branch on the main position number. Assign position numbers, basically. When we describe what's the word? Not substituents. When we describe branches on a particular hydrocarbon chain, we like to describe their position relative to something, the end of the molecule. So the way we name things is that we name from the very end, we started at 1. And okay, fine. So we call either end carbon number 1. But okay, well, how do we know which end to go from? So the way we do that, we name from the side which gives the lowest numbers overall. Well, actually, the way we determine the number, which carbon is number 1, because the carbon number 1 will always be on the end here. It will always be on the end, on either end of the molecule, and we give carbon number 1, basically, we start naming it from 1 to whichever gives the highest order functional group the lowest number. Now, in this case, you'll understand what I mean by that when we go into discussing functional groups, but for now, that's sort of that's the official IUPAC naming thing. So that's the official way IUPAC calls it. You determine carbon number 1 from whichever side gives the highest order functional group the lowest number. So these number here, so for example, if we name from this side, this would be carbon number 2, and this would be 2-methylpentane, whereas if we named it from this side, it would be 1, 2, 3, 1, 2, 3, 4, it would be 4-methylpentane. Numbers may be omitted if unnecessary. I keep them there. And if there's several branches of the same kind, indicate how many there are by using the prefixes di, tri, and tetra. And commas should separate numbers that are grouped together when there are several branches of the same type. So here, for example, this would be 2,3-dimethylpentane. So we call this carbon number 1, 1, 2, 3, 4, 5, so it would be pentane. And then if we name from this side, this is 2, this is 3, whereas if we name from this side, this would be 3 and 4. So 2,3-dimethylpentane, not 3,4-dimethylpentane, because if we name from this side, these methyl groups, which are technically the highest order functional group in this particular molecule, would be given the lowest numbers here, would be given the lower numbers, 2 and 3 versus 3 and 4. Construct the name. So that's sort of how you do it, and then construct the name. You just sort of combine all these rules. If you have multiple sort of hydrocarbon branches, you list them all in alphabetical order. If you have multiple sort of things branched off. You list them all in alphabetical order. So E comes before M, so it would be 3-ethyl 2,4-dimethyl. Yeah, that's sort of a rundown of the naming sort of rules. I'll go into more examples in a later video because this video is already 20 minutes long and there's probably a bit more to do. Yep, there's more. Alright, lastly, we talk about alkenes, which are hydrocarbons that contain double bonds, and their general formula is CnH2n. Ignore the IHD thing, we'll cover that later. And they get the ending "ene" instead of "ane" to indicate double bond. So, and then you number the double bond based on the starting atom that gives it the lowest number. So these are the highest order functional group now, double bonds. So you name it such that you give this double bond the lowest number. You give it the lowest number. So 5-methyl hex 2-ene. The reason why this is 5 and not 2 is because this double bond is a higher priority functional group than this. So we give it the designation it deserves by giving it the lowest number. The last thing to note that is while single bonds have the ability to rotate around freely in space, double bonds do not. I think that's everything for today. Sorry for the long video length. Thank you very much for watching.